everyone, so welcome to our video in Unit 5, Section 3 for potential energy diagrams. So you'll need your notes, pen and paper, and we're going to be talking about how energy is exchanged between endothermic and exothermic reactions, and draw something called potential energy diagrams. Now here's my warning, my stylus is not the best, so I'm going to try my hardest in order to do like really nice pictures for you guys on here, but if it's awful, I will go ahead and just do it in class for you guys as well. But you must still take notes on this and still draw the drawings. I would suggest doing them on a scrap piece of paper so that way it looks nicer in your set of notes. So this is what we talked about in the last video. We talked about the amount of energy it requires in order to break bonds and make bonds. So here for an exothermic reaction, the amount of energy it requires to break a bond, and that's that needs to be having energy in, so the amount of energy it takes in order to break those bonds is going to be much, much smaller compared to the amount of energy being released when new bonds are forming. So when you have more energy when those new bonds are forming compared to how much energy that you have when the bonds are breaking, that's your net energy change, and that's your delta H. So since there's more energy in the products than there is in the reactants, this is a negative delta H. Because we do our products minus reactants and kind of deal with the negative sign. So here again, negative delta H, there's more energy being released by the reaction. On the endothermic side, or the endothermic graph here, we see that there's more energy required to break those bonds then there's actually energy being formed. So this ends up being a positive delta H. And again, an endothermic reaction. So let's talk about that when it comes to the potential energy diagrams. So these are diagrams in which we show how much energy is being used for reactants versus products. These are essentially graphs. So go ahead and draw an X and Y axis. And this is probably the best it's going to get for today. I apologize. So let's go ahead and do some colors. So the x-axis, this can be called several things. This can be called a reaction coordinate or reaction progress. Pretty much all it means is that we'll have reactants and products on either side. So on the left-hand side of that, we show that these are going to be the reactants. The right-hand side are the products. And in the middle, we call that a transition state. A transition between something is pretty much how you go between one step versus another. And that's what we have for this diagram. So it's between the reactants and the products. On the y-axis, we have potential energy. So I'm going to abbreviate that PE, and the more PE, the higher it is higher on the y-axis. So here's how we begin. We start about midway through, and we start to form kind of like a roller coaster. So you're starting to creep up just a little bit more, and then all of a sudden, you go down, and falls down, and then it levels off a little bit more. All right? So over here are going to be your reactants, and these are your products. In the middle is your transition state. We call this middle part an activated complex. By the way, you will need to know how to draw this graph. I will quiz you on it. So I'll give you a blank piece of paper, and you just pretty much go through this. So it just takes some practice. Anyone can do it. It's not a big deal. All right? So that's the reactants, activated complex, and your products. So let's go ahead and start labeling a little bit more of this. So here, this line represents potential energy. So I'm going to write the PE of the reactants. Well, that makes sense because this side is the reactant side, and the y-axis is potential energy, so that whole thing is potential energy of the reactants. Over here on the right-hand side, we can show the PE of the products, so the potential energy of the products. Again, this is when it gets a little hairy and I have to start drawing these. In the middle is the potential energy of the activated complex. So this is when we have the most amount of energy. So with this diagram, we show that we have the products being much smaller, much lower on the graph than the reactants are. So in fact, we can actually just kind of sketch a small little line. In fact, I'll do this line right here and show the difference between them. In fact, I'll do this one up here as well. So we'll show kind of the potential energy of each of these three states. This first one is the product, the second one is the reactants, and the third line up is the activated complex, and it all represents potential energy. So if we take the potential energy of the products minus potential energy of the reactants, that gives us our delta H value. So that's our heat of reaction. So this thing right here, our delta H. And again, it's between the line of the products, the potential energy of the products, and the potential energy of the reactants. So if we take the products minus the reactants, so let's say this is a 1, that's a 2. So 1 minus 2 gives you a negative number. So this is a negative delta H. So you know that this is going to be an exothermic reaction. Okay. So again, because the products is much lower than the reactants, this is an exothermic reaction. A few other little things I want to show you. And again, all these things are things that we have to make sure we put in our notes and any quizzes that I ask you for. Are the activation energy of the reactions. So right here, so if we have the reactants, this is the reactant line all the way up to the activated complex. That's your activation energy of your reactants. So activation energy, and whoopsies. Okay. Activation energy. And again, this is for your reactants because it goes down to that yellow line for the reactants. So we had that same top yellow line right there, except this time I'm going to go all the way down to the products. And that's your activation energy of the products, or the reverse reaction. So activation energy of the products, or we can even say of the reverse reaction. Again, this is when my stylus doesn't work, so hopefully you're listening on to these. Alright, so this is the basic potential energy diagram for an exothermic reaction. You want to make sure that the reactants line is higher than the products line, that this actually ends up, the products go much, much lower, and that your delta H ends up being negative. So, this was for the exothermic reaction. Let's go ahead and draw the endothermic reaction. So, on a little bit lower, let's go ahead and draw our axes again. Alright, and hopefully you can start to fill in some of these. So, we'll have label our axes. We know that we have our reaction progress here. This time I'll call it reaction progress. It's still the same, it doesn't matter. You might see either. These are the reactants, that's still the same. This is the transition state, the in-between state. And this is your product. Okay. Your y-axis, this is still your potential energy. I'm going to write PE. And let's go ahead and draw the diagram. So about midway through, a little bit less than midway, I'm going to go up, 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 up. And then when I come back down, I'm actually going to make it a little bit lower, or excuse me, not go all the way down past the reactants for my products. So in fact, my products end higher than my reactants are. So let's go ahead and draw the yellow lines that go with that. You can kind of see that line right there for the reactant. This is the product, and this is your activated complex. And let's go ahead and label each part of it too. I forget what color I did it in before. I apologize. Let's pretend it's gray. So this is your reactant. This is your product. And up here is your activated complex. I'm going to draw an arrow to it. So let's figure out what everything is. If we show that we have, go to the reactant line, kind of going parallel to that y-axis, this is the potential energy of the reactants. Do the same thing for your product. This is your potential energy of the product. And this is the potential energy of the activated complex. Right. We'll also show the activation of energy of the forward versus the reverse. I don't remember what color I put it in, but we'll just do this color. Alright, so we'll do the reactant. So the reactant line up to the activated complex, wherever that line might be. Again, that's why we show the yellow lines, because we can't quite put it into the curve. So this is the activation energy of the reactants, or the forward reaction. And wherever your products are versus that top line, this is your activation energy of the reverse reaction. Alright, and we also need our delta H. So our delta H is between the products and the reactants. And if we take our products minus reactants, so say for example our products is 2 kilojoules, we'll say it's kilojoules, minus 1 kilojoule, we know that this ends up being a positive 1. That's why this is an endothermic reaction. Okay. So this is the basic potential energy diagram. You will need to know the difference between an endothermic and an exothermic and be able to draw each of them from a blank piece of paper. So what I suggest doing is just practice it a whole bunch of times. Alright, so this is what everything means. The delta H is the heat of the reaction. It's the amount of energy of the products minus the reactant. So let's write the potential energy of the products minus the potential energy of the reactants. You will need to know the activation energy of the forward reaction and the reverse reaction. The forward reaction, we had just said, was the reactants. You will need to be able to label the potential energy of the activated complex, of the products and the reactants, and your axes as well. Okay? So to summarize, an exothermic reaction versus an endothermic reaction. With the exothermic reaction, that potential energy diagram, I'll do a quick little sketch here. This is your exothermic versus your endothermic. Look for where your products end versus your reactants. If your products end lower than the reactants, it's exothermic. If your products end higher than the reactants, it's an endothermic reaction. Make sure you remember all the terms and how to label them, and don't forget to label your axes. Have a good day.